Hello, I am Professor Nagnath Hulle, and in this video we will try to understand the basic concepts about the sequential circuit design, especially synchronous sequential circuit design. In the previous video I have discussed about the prerequisite of the synchronous sequential circuit design, that is how to prepare a table, and which is nothing but the excitation table, and how to make the use of the excitation table for the design process that I have discussed in brief. Now in this particular video we will discuss about the steps required, or this is the procedure of the synchronous sequential circuit design. To begin with, the step number 1. Here we will prepare a state diagram, and we will convert the state diagram into the state table based on the given problem statement. Then step number 2 is we will prepare the state assignment table, means we will assign the particular binary number in the state table or to the state table and find out the number of flip-flops required. Here in this case, this formula we will use, that is capital N is equal to 2 raised to the power of small n, where the capital N is the number of states in the design, and small n is the number of flip-flops required in the design. Means here, if we have the 8 number of the states, then the 2 raised to the power of this small n, and if we are finding the value of the n, this n will become, or n will find to be 3. This here in this particular case, the 3 states or 3 flip-flops are required for this particular design. The number of states required are the 3. Then step number 3, prepare a design table to find out the flip-flop excitation needed. This here we are preparing the design table. In this particular case, we are finding the flip-flop excitation. That is nothing but input needed to the flip-flop to generate next state from the present state. We are taking that into the consideration, and as far as the flip-flops or memory elements are concerned, we have to be very careful about the two things: what is the present state and what is the next state. Here, the output of the memory element or flip-flop is known as the present state of the machine or present state of the flip-flop, and input applied is always known as the next state. Means here, we have to find out the next state, that is nothing but input to the system or input to the state from the present state, that is nothing but from the present state, that is output of the memory element. For this particular case, we have to use the excitation table. Then finally, we are going to find out the simplified equations of the flip-flops inputs and outputs depending on the system specifications, and for this particular case, for the preparation of the equations, we are using the K-map techniques, and finally we are able to build the circuit. These are the theoretical steps required in the design, but these steps are difficult to understand theoretically. Now here I will take one of the simple example, and then we will try to understand this particular design. Here the design statement for this particular design is design a serial adder to perform the n-bit addition. Here in this particular case, expected is that we have the n-bit, n may be the 4. In this particular case, I will take it as a 4. Now suppose we have the number given is 1, 1, 1 and 1. This is A number. And B number, we are taking it as 1, 1, and here it is 0 and 1. This is the number, and we are finding its addition. This is n is the 4. Means this is A0, B0, then A1, B1, A2, B2, and A3 and B3 in this particular case. Here we are using the simple mathematics. 1 plus 1 is the 0, and here is the carry is the 1. 1 plus 1, 0, and here is the carry 1. In the next state, we are adding this. In the next state, we are adding this. That is 1 plus 1. Again, here is 0 and the carry is 1. Now here in this particular case, we have the carry here as 1. Finally, we are adding this 1 plus 1 plus 1 is nothing but 3. And here is sum is 1 and again carry is 1 here. And then finally, 1 plus 1 plus 1 is again sum is 1, and finally we are having the carry as a 1 in this particular case, means this is the summation, and initial carry is always 0. This is. Now here in this case, this is A0, means generally we will use here the shift register for A, shift register for the B, and similar is the shift register to store. This is the sum. This is 0 plus 1 plus 1, this is 0, and this 0 is the sum which is stored here, and then 0 and then 1 and then 1, and finally that can be shifted 1 here, and this will be the final summation available. Now here, what is the basic thing about the sequential circuit design is nothing but the prediction of the number of states. How to predict the state, what do you mean by the state, and what the states forms. Here in this particular case, if you have observed carefully, these things, this is nothing but the carry. This carry we have to memorize for the further addition, and the thing which we have to memorize in that particular case, that will be treated as a state. Means here in this case we are treating the carry as a state. Here as far as the design is concerned, here carry is the state. Now how many states of the carries are possible? Now we have the two options, the carry may be 0 and carry may be 1. Means here in this particular case the number of states required will be the 2. State A, carry is equal to 0, state B, that is carry is equal to 1. And how many flip-flops we need to store the carry as a 0 or carry as a 1? I will use the formula, that is capital N is equal to 2 raised to the power of small n, and here in this particular case it is 2 raised to the power of small n, because we need the two states here. That is here in this particular case the value of the n is found to be 1. Means here in this case one flip-flop is very sufficient to store the carry as a 0 or carry as a 1. Means always the basics about the design of the state diagram is nothing but always we have to find out the number of states required in the design, and that we have to calculate. We are able to get idea from the things which we have to memorize many times. That is in this particular case. I will start with the design of the serial adder, and in this particular case we will go for the design which is nothing but the Mealy design or the Mealy model. Now here in this particular case we will start with the first data, which is nothing but we have the two states, because things which we have to memorize is the carry, and there are the two possibilities of the carries are there. There is carry is equal to 0 and carry is equal to 1. That's why we have the two states. State A, that is nothing but carry is equal to 0, and state B is nothing but carry is equal to 1. Now here this is the present state, that is carry is equal to 0, and we will find out. Now here for this addition 0 plus 0 plus 0, sum is the 0 and carry is also 0. In this particular case the present state is 0, inputs are 0 0. In that particular case output will be 0 and next state will be 0. How we will represent in the state diagram? Now here in this case when we are in the state A, inputs are 0 0, output will be 0 and present state will be 0. That is nothing but present state is the A state itself. We see here in this case if the inputs are 0 and 0, I am using the Mealy model. That's why here its output will be 0, that will be sum will be 0, and next state will be the A state itself. This is the first, and then we will check the similar combination for the same state, that is carry is equal to 0 with different combinations of the inputs, that is nothing but 0 1 1 0 and 1 1, and we will prepare the state diagram first. Now here present state is the A state. In this particular case the input applied is this, that is 0 0. Its expected output is 0, and then we will check it out about its the next state. Next state will be the A here, which I have tried to mention here. And in this particular case now the flow will be something like this, which is nothing but whenever we are in the state A, inputs are 0 0. In case of the serial adder, in that particular case the next state will be the A state. Similarly in the second case, in this particular case present state is the 0, that is A state. Inputs are 0 1. In that particular case sum will be the 0, and the next state will be 0, that is nothing but next state will be the A state. Now here present state is the A, inputs are 0 1. Look at here, inputs are 0 1, which is the input is nothing but xy is 0 1. Output will be the 1, here output will be the 1, and next state will be the same thing, that is nothing but we are in the same state, that is nothing but in the A state, that the next state is the A. Similarly for the third combination of the input, that is present state is the A state, inputs are 1 0, that is again sum is 0, and carry is also 0 is nothing but the next state is again the A state itself. This present state is the A, input is 1 0. Look at here, input is 1 0, output will be the 1, and here the next state will be the B state, sorry, A state, because we are going to remain in the same state. Then here, look at here, the next combination of the input. Present state is 0, that is carry is equal to 0, which is nothing but the state A. Inputs are 1 1. Then sum will be the 1, sorry, sum will be the 0, and C out, that is next state will be the 1. Next state will be the 1 is nothing but B. Whenever we are in the A state and inputs are 1 1, in that particular case output will be 0, but the next state will be the B state. That is the case. Here present state is the A, inputs are 1 1, output will be 0, the next state will be the B, and here this is the flow, and so on. In the similar way we can prepare for the B state. Now look at here, the present state is the B, that is 1, carry is equal to 1 is nothing but B state. Whenever inputs are 0 0, sum will be the 1, and next state will be the 0, means we are coming back to this particular state whenever we have the inputs as 0 0. Here in this particular case output will be 0, and the next state will be the A state, that is 0 state. The similar kind of the things here in this particular case next state will be the A. This is the combination, and then further we have in this case the present state is the B state. Now look at here, present state is the B state, inputs are 0 1, sum will be the 0, next state will be the 1, next state will be the 1 is nothing but we are going to remain in the same state itself. Means here inputs are 0 1, next state will be the B, means we are going to remain in the same state. Similarly for 1 0, the next state will be the B itself, and finally for 1 1, again the present state will be the B. For 1 1, input output will be the 1, and the next state will be again B state itself. This is the preparation of the state diagram. Now look at here, this is the state diagram we have. Means for A state we have checked possible combinations of the input, that is 0 0, 0 1, 1 0, and 1 1. Similarly for the B state we have checked the possible combinations of the inputs, that is nothing but 0 0, 0 1, 1 0, and 1 1. When we have the state diagram with us, using this state diagram we can prepare the next step, that is nothing but state table. Look at here, something like this. Now we have state diagram which I have copied from the previous slide, and using this we can prepare the state table. Now look at the basic things. State A. When the present state is A, the inputs are 0 0. Here we have taken the inputs are 0 0. The next state will be the same state, that is A state, and for this case the output will be 0. This is the output will be 0, or sum will be 0. Similarly, the present state is A, inputs are 0 1. Look at here, inputs are 0 1, output is a 1. Output is a 1, and what is the next state? Next state is the same state, that is the A state. Similarly, when we are present state is the A state, inputs are 1 0. The present state is the A, inputs are 1 0. The output will be the 1. Now look at here, the output will be the 1, and then next state will be the same state, that is nothing but the A state itself. Then when the present state is the A state, inputs are 1 1. Look at here, inputs are 1 1. Output will be 0. The output will be 0, and the next state will be the B state. We are coming from the A state towards the B state in that particular case. These are the things about the state number A. Then state number B, we are checking all possible combinations. When the present state is the B state, inputs are 0 0. Look at here, inputs are 0 0. Output is 1. Here output is 1, and the next state is the A. Present state is the B, and for 0 0 inputs, output will be the 1, and the next state will be the A state. Similarly, present state is the B, inputs are 0 1. Inputs are 0 1, output will be 0, and the next state will be the B. Next state will be the B, output will be 0. Similarly, for 1 0 input, present state is the B, 1 0 input, output will be 0. Present state is the B, 1 0 are the inputs, output will be the 0 and the next state will be the same state, that is nothing but the B state. Whenever the present state is the B state, inputs are 1 1, output will be the 1, output inputs are 1 1, output will be the 1 and next state will be the same state, that is B state, and this is nothing but the preparation of the state table. This is the step number 1, and from this state table we are able to prepare the another table which is known as the state assignment table. Means in this particular state we will assign the particular binary number to this particular state. Now here we have the two states. One is the state A as a present state and another is the state B. We can assign one number to the A, one number to the B. I have here assigned the number to this particular state. A is the 0. This is 0 is the number. And for state B, I have assigned the number as a 1. Number as a 1. Now look at here. For A, number is 0, number is 0, number is 0. Similarly for the B, the number is 1. Then for the state A, number is 0. And finally for the state B, the number is 1. Means in this case, we are assigning only the binary number to each state, and that is nothing but the state assignment. Now here we can prepare the next table, which is nothing but the design table. The difference between the state table and design table is that in this we are adding this particular new column, that is the input to the particular flip-flop. This is the new column, otherwise this is the present state, X, Y are the inputs, this is the next state and this is the sum. We are increasing this particular column in this particular table, and that particular table is known as the design table. Now here we have the state assigned table. Here this is state A and this is the state B, and accordingly this is the state A, this is state B, this is state A, and finally this is state B. Now look at the things. We need to prepare a design table for the selected flip-flop. I have selected here the T flip-flop and I am preparing the inputs as per my selected flip-flop, that is nothing but the T flip-flop. If I have selected D, the design table will be the different. For JK, design table will be different, and for SR flip-flop, the design table will be different. Here we are using the T flip-flop, so we are using the excitation table of the T flip-flop to prepare a design table. This is the excitation table of the T flip-flop. I have considered the states, and here the T flip-flop input to the T flip-flop that I have considered here itself. Now here we will look at about it, how this table works. This is present state, this is the next state, and this is the input, T input required for this particular case. When the present state is a 0, next state we want to be 0. Present state 0, next state we want to be 0, then input applied should be 0. This is the input applied is 0. Then present state is 0, the next state is 0, the input applied is 0 again, the present state is 0, the next state is 0, input applied again 0. Now here the present state is a 0, next state we want 1. Present state 0, next state we want 1. In that particular case, the input applied will be the 1. The input applied is 1, that is input required for the T flip-flop is 1. Means here we are preparing this particular column based on the present state and next state conditions. Now here the present state is 1, next state is 0. Present state is 1, next state is 0. Present state is 1, the next state is 0. The input applied should be the 1. Now look at here, this input applied should be the 1. For 1 and the next state to be 1, the 1 and next state to be 1, input applied should be 0. This is 0. For 1, present state and next state to be 1, the input should be 0. For present and the next state to be 1, the input applied should be 0. Means here we are preparing this particular table, and this particular table is known as the design table, and using this particular table we are preparing the final equations using the K-map. Now look at here the last point. The equations for T input means this. We are preparing the equations for input to the particular flip-flop and output of the flip-flop. T input and sum, that is nothing but output, are prepared using K-map for above system, which has the 3 inputs. What are the 3 inputs we have? We have the inputs as X and Y. These are the basic inputs, and another input is nothing but the present state of the flip-flop, which is nothing but the carry. Sometimes carry may be 0, sometimes carry may be 1. Now here, in this case, using the same table, here, this is the input of the flip-flop, that is nothing but input to the T flip-flop, and this is nothing but the output, that is sum. This is the sum. Now here, we are preparing the equation for T input. Here we have the 3 inputs, that is PS XY, this is PS XY. We are not interested at all this in this NS, we are preparing for this. This for 0, 0, entry should be 0, then 0, then 0, then 1, because here 0, 0, 0, and then it is 1, and so on. We are entering this particular into the K-map, and finally we have this equation. Now similarly we will prepare the equation for this sum. Then entry will be something like this, and we have these equations. And by using these 2 equations, we are able to prepare the circuit diagram. And here, look at, this is the circuit diagram or final circuit diagram. In this particular case, we have the X as the input, Y as the input, and another input is nothing but the PS, that is present state of the machine, which is nothing but output of the memory element is the present state, and input to the memory element is nothing but the next state of the flip-flop. Now here, this is the equations of the present state, and this is the equations of the T input to the flip-flop, that is nothing but the present state, and this is the equations for the output. Means always we have the Mealy design. For especially Mealy design, what is the definition? This output depends on the present state of the machine. Obviously, this is the present state of the machine, as well as input of the system. Here, that's why this is the Mealy machine. And for any digital circuit design, always, or sequential circuit design, we have the format is fixed. This is the state, that is memory element. This is the combination circuit at input side. This is the combination circuit at the output side. Same thing we have here. This is output. Here is the input. We have state here. The input combination circuit is here, and output combination circuit is here. Always this block diagram is similar for each of the digital sequential circuit design. And in this particular case, the final thing will be something like this. And thank you for watching this particular video, and in the next video I will consider the same circuit, that is design of the serial adder by using the another concept, which is nothing but the Moore circuit design. I have considered here the Mealy design, and in the next video I will discuss about the Mealy circuit design. Thank you for watching this particular video. That's all.